Okay, thank you so much, Yang Yu. Thank you very much to everyone. Can you all hear me? I think the mic is on. Okay. All right, so I want to talk, this is a topic in effective descriptive set theory, really, and I'm going to talk about ranks. So you're probably familiar with ranks. It's the notion of, that appears very often in descriptive set theory. That's one topic, and it's somehow connected to complexity of Borel codes, and I want to explain in this talk why, in this case, these are connected. They seem like two different problems, right? And mainly, the idea of my talk is I want to really get to some interesting open problems. That's the motivation. And this is from a paper. It's not so very recent, but it was recently accepted. It's with Philipp Welch and Merlin. It's a joint project. All right, so let's start with effective descriptive set theory. So we have, so unfortunately in my slides, I can't distinguish between boldface and not boldface, sorry. So I guess these sigma 11, pi 11, they're always going to mean without parameters on my slides, all right? But you can't see the difference. While when I talk about Borel sets, I'm going to allow parameters, right? So the sigma 1 and pi 1 are light phase classes. So we take, for pi 1, well, the effective class is the set of branches through a computable tree, and then the projections of those are sigma 11, equivalently given by sigma 11 formula. Sorry, this should be a 1 here. All right, but I'm sure you know this. As I said, these will be the effective classes. All right, so we work with various assumptions, usually in ZFC when we study analytic sets and sigma 1, sigma 1, 2 sets. We sometimes need things like sharps for reals. That's the strongest assumption I'm going to use. And actually, we didn't study any reversals, although this conference on reverse math. So here are just some examples of well-known reversals. For example, the pi 1 perfect set property. Now I mean the boldface one means it's actually equivalent to omega 1 being inaccessible to reals. So inaccessible in every L of a real. And then sharps for reals equivalent to boldface sigma 11 determinacy. All right, so the way many people think about pi 11 sigma 2 sets is actually given by a computation. That's often very useful. So you can think of a pi 11 set as given by, so you have an input, a real, and you're trying to test whether it's in this pi 11 set. And so you can run this computation of length less than omega 1 ck relative to the input. Think of some kind of infinitely long computation. I'm going to explain in a second what it is. And every pi 11 set can be represented in this form. All right, and for sigma 1, 2 sets, you can do the same. It's just that you can go higher. You can go up to any countable ordinal. So the one for pi 1 we've already seen in another talk is the Spector-Gandy theorem, essentially. It says that pi 1 is the same as sigma 1 up to this ordinal. All right, so just think about some kind of algorithm that runs along the levels of L for that. And just to give a more concrete example, some people, as you know, study particular machine models that that describe particular classes in between pi 1, sigma 1, 2. So this is the example is the infinite time Turing machines. So it's like a Turing machine, and we have this this head that moves along the tape. It behaves like a standard Turing machine. And what does it do at limit steps? Well, in this model, you jump back to the first cell, and there's a special limit state, and then you just continue computing. And the information is not lost because in every cell you take the lim_inf of the previous values. And then one can show that with this one can actually compute certain levels of L. So it's equivalent to just thinking of L up to a certain level. It's a bit higher than omega 1 ck in this case. All right, but this is just an example, and the reason why I mentioned this is because this is how I think of ranks. I think it's very useful. So first, let's look with this kind of model. Let's say a set is semi-decidable for this model. If there's an algorithm for this kind of machine that halts if and only if the input is in that set. And as you can see, this kind of layers the set into simpler sets according to the halting time. And that's called a rank. So that's how I think of a rank. So we have the set A, and it's layered into simpler sets. And then what is a rank really? Well, the point is that not only the layers are simple, but the comparison between them is very simple. So if you have two reals, x and y, then you can tell in a semi-decided way. So you can decide on, well, you have an algorithm that halts if and only if this relation is true. So you can compare whether the algorithm halts on x before it halts on y, where it doesn't actually have to halt on y. It could also diverge. And we also have a strict relation. All right, so this is how I think of a rank. This is the definition of a rank. It's just, in general, you have a class of sets like pi11 or sigma12. And then the rank layers the set by, so the layers are themselves in the dual class. They're simpler. And then you have these two comparison relations. They're restricted to the set they're agree with a certain pre-well order. And then also, if you have x and y, one of them is A, the other one is not, then like all the rest is sitting on top of everything in A. All right. So this is from descriptive set theory. And the class is called, has the rank property of every set in gamma, has a gamma rank. And well, this is very important in descriptive set theory because one thing is you can prove reduction and then the separation property for sigma-1,1 sets, for example, but also for many other classes. All right, and I just want to mention that I always think of a machine giving you a rank, but this is actually a bit more restricted notion of ranks. Like not every, even for this class, not every rank is given by a machine. There are some counterexamples. All right. So I'm going to give you some examples. So ranks appear everywhere in descriptive set theory all the time. So here's the most basic rank. We take all well orders on the natural numbers, then we order them by the order type, W alpha. That's the pi11 rank. Next one is the Cantor-Bendixson rank on all. This should, of course, say closed sets, not countable. So on closed sets, so you form derivatives, like you remove isolated points in an iterated way, and then at some ordinal, this process is going to stabilize, and that's called the rank. And so the set of trees, I guess, is a pi11 set, and it can be written as a union of Borel sets in this way. Here's just examples. Here's another one from. That's an interesting rank on the set of differentiable functions understood as a subspace of the continuous functions. So you can measure, so the derivative removes points where the function is close to being differentiable. So for example, this rank is built so that continuously differentiable functions have rank 1. So if you just do one derivative, you remove points where f is very close to being differentiable, you remove everything. So this means rank 1. Again, so there's this pi11 set, and it has a natural rank. Just an example. We don't need it. All right, but there are actually many other ranks appearing everywhere. For example, on certain classes of groups, people study ranks, certain classes that are pi11 sets. Very useful. Okay, so what's the problem of my talk in this project? So we asked ourselves, if you look, like many typical ranks have length omega 1, like the ones I showed you. But you could look at countable ranks of countable length, and we just ask ourselves, how long are they? So which countable lengths are possible for such ranks? And we computed the supremum of this. Then you could ask yourself, which sets, so you look at the underlying set, which sets actually admit a countable rank. So somehow this should say that the set is simple. This is very easy for pi11, but becomes more complicated for sigma12. And then there's a related question. I explain how simple are Borel codes for pi11 and sigma12 sets. So what I mean, so these are light phase classes. So you could have a pi11 set defined without parameters that happens to be Borel, right? And then you could ask if you, well, you know it's Borel. Let's say it's delta 0 alpha, and in addition, you know that it's also pi11 without parameter. Does this tell you something about the Borel code? All right. So let's start with the easy case pi11 set. So, first, if you take a pi11 set and you already know the set is also Borel, then the rank is always going to be countable. Why is that? Well, that's this part here. Well, we have the set A that's Borel as well. We have this rank on it. Then we actually get a sigma11 pre-well order if you add this infinity class on top. And the Kuhn-Martin theorem says that, that analytic well-founded relations have countable length, so they're countable. But conversely, if we take any such rank is countable, but if you take any pi11 set that doesn't have a countable rank, then it's also Borel. So this is an if and only if. Why again? Well, it's clearly Borel because it's the layers are Borel and they're countably many, right? So this is equivalence. Right. So here you can see why Borel is related to the question of ranks. And so to say a little bit about the ranks, let's look at these interesting ordinals that I'll just call sigma alpha n. But if you want, you can forget about alpha. You can set alpha to be 0. And let's see. So let's just set alpha to be 0. And it's just the soup of sigma1 definable ordinals, the soup of sigma2 definable ordinals, and so on, within L omega 1. So the real omega 1, not the omega 1 of L. Right? And we're interested in particular, actually only in the first two, so the soup of sigma1 definable ordinals over L omega 1, and the soup of sigma2 definable ordinals over L omega 1. Right, one can also show some equivalences, like instead of sigma2, you could put pi1, for example, it's the same. And then it's also, this is equivalent to the least ordinal satisfying a kind of submodel criterion. So it's the least ordinal that this, we don't say it's a submodel, sigma1 or sigma2 submodel, but it satisfies Tarski's test. So Tarski test says, if you have a sigma n formula with that's true in the larger structure, then it has to have a witness in the smaller structure. But I mean, that's true for every elementary substructure, but we don't allow parameters, right? So it might be weaker. All right, so, and maybe some people are familiar with so-called sigma n stable ordinals. Have been used a lot. It looks like it's almost the same. So sigma n stable means sigma n elementary in, we're going to put L omega 1 here. And it is equivalent for sigma 1, but not for sigma 2. So I put the argument here for sigma 1 to see that the sigma, so the soup of sigma 1 definable ordinals is actually the least ordinal. That's sigma 1 elementary substructure. Well, okay, since I have it here, why? I'll explain how. So it's very simple. So first of all, our ordinal is, so this ordinal clearly is elementary, so it satisfies Tarski's test. But conversely, we want to show, it suffices to show that if you look at this L gamma, so the least one, so that's sigma 1 elementary and L omega 1, it suffices to show that every element is sigma 1 definable. The element of this thing, then they're all going to agree. Yeah, but this is kind of clear. So take all the sigma 1 definable elements of this, call this M. This M is going to be a substructure. We're just trying to show M is equal to L gamma. But if not, then you can take the transitive collapse. I'm just going to move something, this X. But remember, everything is sigma 1 definable, also this x, but now it's moved by this map. But it's still defined by the same formula. But that can't be. And now, I mean, because by sigma 1, absoluteness is defined, satisfies the same formula in D. All right. So this fails for sigma 2 here, and it's wrong for sigma 2. So tau was the super sigma 2 definable ordinals, and it's not necessarily, this L tau is not necessarily a sigma 2 substructure. It is, that happens if and only if omega 1 equals omega 1 of L. So this is just to compare it with, I want to compare these with the stable ordinals, right? So, so the fact that this is sigma 2 elementary substructure is equivalent to omega 1 is omega 1 of L. There's some other equivalent statements, for example, L tau is sigma 2 admissible, and tau is the least one that has, the least ordinal that has the same sigma 2 theory as L omega 1. Right, this is another ordinal, but happens to be the same here. I see. I think this one should be 2, but I'd have to check. But I think it should be 2. I don't think we got, I mean, sigma 3 seems too much. But it might actually be sigma 1. Might be sigma 1. Yes, I do, but I might have made a mistake. But I'm pretty sure it's not sigma 3. But I might have made a mistake here or here. Not sure. Thanks. And there's some other characterization, but this was just to compare. So we want to know about these ordinals because of the ranks, so let's just see what they do. So sigma is always, it's absolute, but this tau changes if you go to different models of set theory, for example. So this is the case we just saw. If omega 1 of L equals omega 1, then this tau, well, is clearly countable, so it's somewhere here. But if the omega 1 of RV is actually, if that's above omega 1 of L, then tau is going to be pushed up here. And again, same for omega 2 of L and so on. So this ordinal is variable depending on the model you're working with. And then you can compute the lengths of certain of these pi11 ranks, sigma 2 ranks. Those that are countable, the supremum is precisely tau. And well, I mean, one step of the proof is to construct long ranks. I won't say anything about that. And the other one is to bound them, and this is by just bounding sigma 1, 2 well-founded relations. And you know the Kuhn and Martin theorem, I guess. So this is like it's something very simple, but it's a version of the Kuhn-Martin theorem for well-founded sigma 1, 2 relations, assuming the rank is countable. So, of course, in general, these might have rank omega 1 or something above omega 1, but if the rank is countable, is below tau, and tau is the supremum of such. And the idea to prove this is just a kind of simple absoluteness argument. So we consider the pi1 formula saying that. So we want to express that the relation has rank at most alpha, this relation here. Alpha is countable. And so to do this, we say that we want to express the summa by pi1 formula. So we're going to say that in any transitive model of ZFC, the rank is at most alpha. So model containing this alpha. That's equivalent. And then we go to a certain generic extension, making alpha countable, and do an absoluteness argument. And then we can reflect this formula below tau. This is this Tarski test property. You can reflect sigma 2 formulas below tau. All right. All I wanted to say about that. All right, so then here are just some results that computations one can get out of this. And then there are certain pre-well orders we computed the suprema of certain types of pre-well orders of this form. And well, to show this, you always need to construct certain long pre-well orders of this form. And there's this periodic pattern here. And as you see, it's very important what's the domain of the free-will order, for example. Let's see, for example, compare this one. Sigma 1 strict sigma 1, 2 pre-will orders onto the omega. But here we have just pre-will orders, so that's the non-strict versions, and they have completely different suprema. So the lengths here are at most tau, actually below, and here we are above the first silver indiscernible that I called Yoda 0 here. So I'm assuming that 0 sharp exists here. And here's an interesting question. I don't know if these three suprema are the same. So that kind of computation goes beyond what we do, because I think you need stronger assumptions than that, like certain determinacy assumptions. All right, let's go back to the problem. Second problem I mentioned, which sets admit countable ranks. So we know this one for pi1 sets is very easy. And what about an analog for sigma 1, 2? So does a sigma 1, 2 set admit a countable rank if and only if it's Borel, for example? Well, the problem is both implications fail. So as you can easily see, for example, I mean, clearly you can, if you have a delta 1, 2 set, it has a rank of length 1, and it doesn't need to be Borel, so the implication from left to right fails. So here I'm arguing that the implication from right to left fails. So let's take, just for example, 0 sharp. It's a pi1, 2 singleton. And we take his complement. This is sigma 1, 2 set. And I claim it does not. The set is the complement of singleton. It's light phase sigma 1, 2. I claim it does not admit a countable rank. Well, clearly it's Borel, so it's a very simple Borel set. And why this is because of this lemma. If you take a finite or countable pi1, 2 set, in this case the singleton, and its complement admits a countable rank, then it has to be in L already. Let's see if I have. Right. So it seems like this fails, but really I'm interested in to make it work, make this work. So we have to somehow change this problem a little bit. So maybe the problem is that this singleton is a bad Borel set. I think it's bad it doesn't have a code in L. So we could restrict to sets with Borel codes in L. But then we have to ask, does every pi1, Borel set have a Borel code in L? This should be true, but that's not actually true because, for example, take a counterexample to the pi1 perfect set property in L, then go in an outer model where the omega 1 of L is countable. So this set actually doesn't get any new elements, so it's going to be a countable pi1 set. But of course, it doesn't have a Borel code in L because it's uncountable there. Right, so this fails. But that's no problem. We can just go to Borel alpha code. So this is, in this case, from the viewpoint of L can't see the set is countable, but L can just enumerate the set. It's just omega 1 of L many elements. So this is from the outside, it's an F sigma set. But L doesn't see that. But we can just take alpha to be omega 1 of L and then say, well, it's still a Borel set, but we just allow unions of this length and intersections. Right, so then we have codes of this form. So they're just functions from, you fix an ordinal alpha, and then Borel alpha code is just a function from alpha to 2 that codes a certain set, where now, as you can see the differences, you can form, if this is omega 1, you can form omega 1 unions, and so on. So now the question maybe is better. Well, a pi1 Borel set, it does have Borel alpha code in L for some countable alpha. So the alpha is countable in V, but not in L. It's a proof sketch, but I don't, well, I'll just say what's the idea. Well, our set is pi1, so it's the preimage of the set of well orders by a function f, but it's also Borel, so the image is an analytic set, and that's bounded by some alpha. So therefore, we have upper bounds, and the set of upper bounds is pi1, 2. And then using essentially the definition of our ordinal tau, we can actually get a bound below tau. And then our set is reducible to actually two well orders of a short length, and that set itself has a simple Borel code. All right, and I also want to mention this proof does not provide a quantitative result, so of course it would be more interesting to ask whether any pi11 set that's additionally sigma 0 alpha has a sigma 0 alpha code. Yes. No, yeah, I just meant precisely that, like a local result for sigma 0 alpha. So does every pi11 set that's Borel in particular, let's say it's sigma 0 alpha, we know it has a Borel alpha code in L, but can we choose that code with the same complexity? And it is true with additional assumption by a result of Stern. I'll mention it's quite a nice result. All right, but now the problem becomes, if you take a sigma 1, light for sigma 1, 2 set that happens to be Borel, does it admit a countable rank if and only if it has a Borel code? And this should be alpha Borel code here, sorry. So we only have very partial results about this. So let's just start with countable sets. An example for an F sigma set. First of all, by the Mansfield-Solovay theorem, countable sigma 1, 2 sets are contained in L. So it's true for those. And the first interesting case is a countable pi1, 2 set. And so here's an equivalence. A countable pi1, 2 set is in L if and only if it's in the small piece of L. If and only if it's contained in a countable sigma 1, 2 set. If and only if it's contained in a countable delta 1, 2 set. That's easy to show. And the point here is that it's also equivalent to 4, and forces that there is a countable rank on the complement of this set. So this is exactly what we wanted, except that I'm using some additional assumption. The assumption is that one of three things. It's true if omega 1 of L, omega 1 is omega 1 of L. This is true if omega 1 is inaccessible to reals, so it's inaccessible in every L of a real. And it's true if sigma 1, 3 generic cone absoluteness holds. And so it's actually quite hard to find models where this proof doesn't work. So I only know of one model where the proof doesn't work. So there I don't know. There I don't know whether this results hold. But yeah, but I don't know. We don't have the general result. Okay, again, this was the problem that we now came up with. You take a sigma 1, 2 Borel set. Does it have a countable rank? If and only it has a Borel alpha, that should say, and code in L. And as you can see, if you want to prove that, we first need to, let's see. I mean, in particular, delta 1, 2 sets, of course, have ranks of length 1, so we need to prove it for those, and that's already non-trivial. So let me first mention result on one level lower. That's Louveau's separation theorem. We're familiar with. So it's a version of the separation theorem for sigma 1, 1 sets, except it says that in addition, we know that the set is sigma separated by a sigma 0 alpha set. So in general, they can be separated by a Borel set, but we know the level of the set. But then Louveau proved we can actually pick a set with an hyperarithmetic code. Very simple sigma 0 alpha set. You can see this is analogous to what I was saying before. But just in our setting, we're interested in codes in L, not in L omega 1 CK. So in this setting, the analog is L. I just put the proof so that you can proof sketch so you can see it's an induction that uses the topology generated by like a sigma 1, 1 set that came up in Dominique's talk already. But it's a modification, so the you take sigma 1 sets there that are additionally pi 0 alpha. And there's no way the proof generalizes because it uses pi 1 1 uniformization, and we don't have pi 1 2 uniformization. But this result was actually proved a long time ago under assuming that omega 1 is inaccessible in L. So this is a very nice result that I want to quickly explain here. Let's see. Let's go to the theorem here. So we have two disjoint sigma 1 2 sets, A and B, and they can be, we assume that they're separated by a Borel set of level alpha. And he showed that they can already be separated by a set with a code in L. But the only problem is that this ordinal here might be a bit large. And that's why he simply assumed that omega 1 is inaccessible in L, because then this ordinal here is countable in V. Right, so this is actually a Borel set in V. And this is a very nice absoluteness argument that works by essentially collapsing omega 1 and then applying Schoenfield absoluteness in a way. And he shows this equivalence between these kind of Borel sets from the viewpoint of V, and from the viewpoint of the model, they're kind of described by a forcing. So they're given by a name inside the model that, so in the model you have a name for an actual Borel set, and then in the universe around it, this describes a different set. All right, so really my main question is, one of the main questions is, does this just hold in ZFC? This was part of the previous problem that we arrived at. And so here's some very partial results at the end of my talk for this. So we just came up with some particular cases where it does hold. For example, let's so it's clearly true in the constructible universe, because then the code's already in L. Now let's force over L by a proper forcing, and then it's still going to be true. Why? Because a proper forcing cannot add proper forcing cannot add any new delta 1 2 Borel sets. So if the forcing adds such a code, then this set already had a code in the ground model. That's what one can show. So these are Stern's result shows this is true in models that are kind of large, far away from L, and this model is very close to L, right? So what about, it's already surprising, so that's why I think it might be possible in general. It's just hard to find counterexamples. Also, let's take something in between, we just collapse any cardinal, then it's still going to be true. We take, over L you collapse any cardinal, call omega kappa. And here's another particular result just for sigma 1 2 from a weaker assumption, sigma 1 3 generic cone absoluteness. Right, so I think this problem is interesting. I don't know how it will turn out, because it's true in all models that are far away from L, but it's also true in models that are close to L, so it's kind of unusual. Right, and so the only model I could come up with where the proofs don't actually work is an extension where, for example, by omega 1 number forcing, it's a way of collapsing omega 1 in a different way than normal. And you do usually. But I don't know. All right, so that's my last slide. Right, this was the question that I'm interested in. Does any delta 1 2 Borel set have a constructible code? The quantitative version of this would ask, if it's a sigma 0 alpha set, then can you also find a code that's sigma 0 alpha? And so I think it's interesting because it relates to various known results. For example, I could think of Schoenfield absoluteness as saying that any pi11 singleton is an L, right? Because, I mean, assuming that we know about pi11 uniformization, it's equivalent to saying all pi11 singletons are an L. So these are particular simple pi11 sets. The Mansfield-Solovay theorem says that countable sigma 1, 2 sets are an L. Again, very simple sets. And we're asking about Borel sets. Our question is really can be understood as a version of the Mansfield-Solovay theorem for Borel sets, right, instead of countable sets. And this is the lemma I mentioned about pi11 Borel sets. That's essentially from paper of Kekris, Marker, and Zami. And Stern proved a very general result. It just has this additional assumption, unfortunately. And there was some recent result where showing that Cohen randomness X-force doesn't add delta 1, 2 Borel sets, and we proved that's true for proper forcing. Do that? Anything more? That's just literature. Okay, thank you.